just didn't think that you had enough mathematics in this course. So here are some properties of stars and what they depend on. And so the first one says that the R, the radius of a star, is proportional. So that symbol there actually means proportional. It's not an equal sign. So it's proportional to m, which is the mass of the star. So if this had been an equal sign, there'd be other constants and letters on this side over here. Let's not worry about it. All I want you to see is that the radius of a star depends on its mass. Now we could even go further, because I could say if the mass of a star was bigger, what would be the radius of that star? It would be bigger. We could go even further. We could say if the mass of a star was to double, what would happen to the radius of the star? It would double. Okay, so these are some things I think that you ought to know for the exam. If I give you the formula, you should be able to interpret what it means. Okay, the second equation deals with the letter L. So that was the luminosity of the star. So that was its brightness, actual brightness. It was also the amount of energy that this star gives off every second. And it is going to be proportional to m to the fourth power. Now this is kind of unusual. I think that you would have known that if a star has more mass, it would be brighter. But you might have thought that if you doubled the mass of a star, it doubles the brightness. But it doesn't, because it's raised to the fourth power. Okay, the next one is going to be the temperature of the star, but notice that this is the temperature at the surface, and it is going to be proportional to m. And then the next one is going to be the temperature in the core, and it is going to be proportional to the square root of m. So notice that the larger the mass of the star, the hotter the star is going to be, both at the surface and at the core of that star. So the one that might be unusual to you is going to be that last one. So you should know that T stands for time. So this is going to be the lifetime of the star. So how long is the star going to live? Okay, so that's what this means. And it's kind of unusual because it's proportional to 1 over m, and then raised to the third power. So not quite the equation that you thought it was going to be, because I bet you that you would have thought that the more massive a star is, the longer it's going to live. Because let's say that we're talking about cars. The bigger the gas tank on a car, the further the car can go before it runs out of gas, right? Well, not necessarily. Okay, so let's use this analogy here, and let's talk about the lifetime of stars. Okay, so I've got this analogy between the M1, the Abrams tank, and a Volkswagen. So notice that the mass of the M1 tank is very, very large compared to the mass of the Volkswagen. Okay, let's look at the fuel tank. So the fuel tank is 504 gallons for that M1 tank, and it's only 12 gallons for the little Volkswagen. All right, so why does that M1 tank need to have such a large gas tank? Well, look at the MPG, miles per gallon. A M1 tank can travel 0.6 miles for every gallon of gasoline that it uses up, whereas that Volkswagen has an MPG of 30 miles per gallon. Okay, why? Okay, the M1 tank has to push, it takes a lot of force to keep that tank moving because it's so heavy. whereas it doesn't take as much energy or as much force in order to propel that Volkswagen Bug. Okay, so that if a star has a lot of mass, that means it also has a lot of gravity. So in a star, the mass of the star is what causes gravity, which is trying to crush that star and turn it into a black hole. So that means that that star has to work extra hard, pushing all that extra mass back out and keeping gravity at bay. So therefore, a large star is going to use up its fuel faster than the little one is going to do because it's so large. It has to fight that gravity constantly. All right, so let's go back to here. And the main thing I want you to get out of all of these different equations is that the number one thing that is going to determine the fate of a star is going to be its mass. So the mass controls the size, the energy output, the temperature, and how long it's going to live before it dies. So that's the number one thing I want you to get out of this. Now, you might be saying to yourself, well, what are some typical masses and typical radiuses and all these other properties? I'm glad you asked, because here we go. So this sample calculation, you notice it says you will not have to do this on the exam, but what I did was I picked various masses. I picked a very, very small mass, and then a small mass, and then a mass like the size of our sun, and then a larger mass, and then a very large mass, and a very, very large mass. Okay, and then I took all of those masses, and in terms of the sun, so the sun would have a mass of 1. And then I said, well, what about if it had a mass of like only 0.04? Then what would happen? So I took those numbers and I plugged it in this formula, and so you can see how would the radius of these new stars be compared to the radius of the sun. How would the brightness of these stars be compared to the brightness of the sun, and so forth. So if you want to look through that, then go ahead, but you're not going to have to do any of those calculations for the exam. Okay, let's take a break. When we come back, we're going to start with very, very small stars and then talk about what happens to them.